Let's look at the critical connection between measurement error and the process of establishing validity in research. First, it's vital to understand that unreliability in measurements sets a ceiling on the correlation among variables. That means if our measurements are not consistent, the correlation will not be constrained, never reaching its full potential. In essence, the less reliable the measure, the more suppressed the correlation. The observed correlation, denoted by R sub xy, represents a lower bound for the actual correlation between the true scores of x and y. Interestingly, this observed correlation is equivalent to the true score correlation if and only if x and y are measured perfectly without any error. However, in real-world scenarios, achieving perfect reliability is rare, if not impossible. The reliability index, calculated as the square root of the reliability coefficient, serves a unique purpose. This value acts as the upper bound for the criterion correlation, symbolized by rho sub xy. Essentially, this index helps us understand how far our observed correlation might be from the true correlation between x and y. Finally, we must appreciate that while reliability is crucial, it's not everything. Reliability is a necessary condition for validity, meaning that without consistency in our measurements, we cannot have valid results. However, it's not sufficient on its own. A measure can be reliable without being valid, like hitting the same wrong spot repeatedly. For true validity, we need both accuracy and precision, hitting the right target consistently. Every researcher understands that no measure is perfectly reliable. This reality is particularly complex when we deal with abstracts or complex phenomena like body image or self-esteem, where the constructs themselves may be challenging to define precisely. In real-world research, both predictors and criterion can be highly error-prone. It might be because of the subjective nature of what's being measured. What does it really mean to have a positive body image? What might be a positive body image to one individual might not be the same for another. These ambiguities can reduce the correlation between predictor and criterion, or in statistical terms, attenuate the relationship. Consider evaluating a treatment program for individuals suffering from serious self-esteem and body image issues. The complexity of these issues and the nuances of individual experiences can introduce significant measurement error, affecting the validity of the research conclusions. Consider the evaluation and treatment of suicidal behavior and self-harm. Often, self-harm and suicidal behavior are symptoms of deep-seated emotional distress. Accurate measurement of these underlying causes is essential for early intervention and support. Tailored strategies for prevention and treatment require a nuanced understanding of individual experiences, again, highlighting the importance of accurate measurement. Measurement error and the consequent attenuation of correlations between predictor and criterion variables are not just statistical issues. They have real-world implications. If left uncorrected, attenuation can lead to the underestimation of the relationship between key variables, potentially undermining the effectiveness of interventions. Errors in measurement can misguide policy decisions, allocation of resources, and clinical treatment strategies. Correcting for attenuation is a nuanced process, requiring careful consideration of the reliability coefficients of both predictor and criterion variables. This involves the following steps. First, calculating validity coefficients, using formulas to adjust correlations for the effect of unreliability. The correction formula is rho sub xy divided by the square root of rho sub x times rho sub y. Rho sub x and rho sub y are the reliability coefficients for the predictor and criterion, respectively. It's crucial to use high estimates for the reliability when applying corrections, as underestimating reliability means you'll overcorrect. This correction should only be applied to validity coefficients and not to every correlation. Let's look at a real-world example. Dissociative symptoms can be complex and multifaceted, often manifesting in various ways. The dissociative symptom scale and the dissociative experiences scale are tools used by mental health professionals to understand these symptoms. Correct assessment is vital for the diagnosis and treatment planning. Let's explore how validity and reliability come into play. The correction formula used here is going to be from the previous slide, rho sub xy divided by the square root of rho sub x times rho sub y, where rho sub xy is the original correlation between x and y, the DSS and DES score. Rho sub x is the reliability coefficient alpha for predictor x, which is the DSS. Rho sub y is the reliability coefficient alpha for criterion y, the DES. Let's look at some sample calculations. Let's say alpha is 0.94 for DSS and 0.95 for DES. We'll end up with rho sub xy being 0.63, meaning this is the validity coefficient. This means that there's a substantial correlation between scores on the DSS and the DES. But is this the entire story? This is like saying that 63% of the time, when you aim at a target, you hit close to where you intended. In this context, it tells us that the scores on the DSS and DES are related to each other about 63% of the time. Looking at our initial validity coefficients, rho sub x is 0.94, which is the alpha for DSS, and rho sub y, again, is 0.95, which is the alpha for DES. Alpha is a common measure of reliability. Here, when we see the two that we have, think of alpha as the quality of your bow and arrow, or whatever you're using to hit the target. If they are top quality, 0.94 for DSS and 0.95 for DES, you're likely to hit closer to your target. Using the correction formula, this accounts for unreliability in measures. Sometimes, even with the best bow and arrow, you might not hit exactly where you aimed due to wind or other factors. This formula helps adjust for those external factors. That's unreliability. When we plug into the formula, we get a corrected correlation of 0.67. So after adjusting for those external factors, we find that our actual aim is closer to 67% accurate. This corrected number tells us more precisely how related the DSS and DES scores are. Well, what if alpha for DES was 0.8 instead? This means that if the quality of your bow and arrow for DES was lower, that's like having 80% quality instead of 95%, then we do some recalculations. Rho sub xy is still 0.63, rho sub x is still 0.94, and again, rho sub y is now 0.80, the alpha for DES. When we use the formula again, we get approximately 0.73. So we find that our actual aim is 73% accurate. However, our work is not done as we need to look at the differences in percentage increases. The percentage increase is calculated to show how much the corrected validity coefficient increases compared to the original. For scenario 1, it's going to be 0.67 minus 0.63, all divided by 0.63, giving us about 6%. For scenario 2, it's going to be 0.73 minus 0.63 all over 0.63, which is going to give us about 16%. These percentages represent how much more accurate our understanding is after making these adjustments. It shows us that our original estimate was off and that considering the quality of our tools, alpha, can significantly impact our understanding of how two things are related. So why these formulas? These calculations are used to correct for the measurement error in the predictor and criterion. Since no measure is perfectly reliable, this correction helps us give a more accurate picture of the true relationship between the predictor and criterion. By correcting for these errors, we get a more honest representation of the relationship between DSS and DES. The percentage increase helps to show how significant the changes in reliability coefficients are. It quantifies how the reliability of the DES affects the overall correlation and therefore how carefully the reliability needs to be considered in real-world applications. We need to think of the ethical considerations in correction. When attempting to correct for measurement error in statistical data, researchers often use reliability estimates. These estimates help to adjust the correlation coefficients to better represent the true underlying relationship between variables. Using high estimates for reliability can help in being conservative about corrections, ensuring that the changes are grounded in strong evidence. However, going too far in this direction can lead to overcorrection. This might mean that the corrected results are too optimistic, overstating the true relationship between variables. Overcorrection can create a false sense of precision and accuracy. If overcorrection occurs, it can mislead other researchers or practitioners or policymakers who rely on this information. This, in turn, can lead to wrong decisions, incorrect theories, or ineffective interventions. Researchers have a moral obligation to handle these corrections with care, weighing the need for accuracy against the risk of overestimating the relationships in question. Transparency in research refers to the clear and complete disclosure of all aspects of the research process, from data collection to analysis and interpretation. Transparency is particularly crucial when correcting for attenuation due to the measurement error. The exact methods, reliability estimates used, reasons for corrections, and any assumptions made must be clearly stated and justified. By being transparent, other researchers can understand the process used, evaluate its appropriateness, and potentially replicate the study. This builds confidence in the findings and fosters a more robust scientific community. The methodologies must be clear, and the reasoning behind the corrections must be robust. This ensures that the corrected results truly represent an improvement over the raw data and are not simply the product of arbitrary decisions or manipulation. Transparency also holds researchers accountable for their choices in the correction process, encouraging rigor and maintaining the integrity of the research process. Recall that construct validity is about ensuring that the tool or method we use in research measures exactly what it claims to be. Additionally, recall that CFA is a statistical technique that lets us test our assumptions about how a set of observed variables reflects a set of underlying hidden variables, which we know are called latent variables. It's like building a puzzle. The observed variables are the pieces, and the latent variables are the complete picture we're trying to build. CFA helps researchers ensure that their tools and assessments align well with the theoretical constructs. In clinical terms, these latent variables might represent underlying mental health conditions, such as depression or anxiety, that we can't observe directly. Using multiple observed indicators, which are questions, symptoms, or signs related to the construct, like depression, the CFA helps us understand how closely these indicators align with the underlying reality, the actual level of the mental health disorder. The correlation among latent variables helps us obtain an error-corrected estimate of the validity coefficient. Think of a survey measuring stress levels. The individual questions, which are observed indicators, might ask about sleep quality, appetite, mood, etc. By correlating these, CFA helps us see the big picture of stress, which is the latent variable, in the individual. These indicators can be different kinds of measurements, from single survey questions to groupings of similar questions. And those are item parcels. And now we need to understand item parcels. Instead of using individual questions, sometimes we combine related questions to form item parcels. It's like baking cookies with different combinations of ingredients to create unique flavors. For example, in a depression scale, instead of 12 individual questions, you could group questions about mood, appetite, and sleep into 4 separate groups. Those would be the item parcels. Think of a clinician assessing a patient for anxiety. They might group questions related to physical symptoms like heart rate, sweating, cognitive symptoms, which would be worries and fears, and behavioral symptoms, which would be avoidance and restlessness, into separate parcels. For a single indicator, sometimes the criterion is straightforward and does not need complex analysis, like a simple pass-fail result in a medical test. For a clinical example, did the patient receive a specific diagnosis based on a clinical interview? But there are challenges with dichotomous variables. The standard Pearson formula might underestimate relationships involving dichotomous variables, such as yes/no answers. The solution is, when dealing with dichotomous variables, it might be more appropriate to use the polychoric correlation, a statistical method that considers the underlying continuous nature of dichotomous data. A clinical example for understanding the polychoric correlation, well, this statistical method helps us dig deeper into the yes/no type questions. It can be crucial in understanding mental health symptoms that aren't simply black and white. Assessing levels of daily functioning in patients with schizophrenia, a simple yes/no won't capture the complexity. Instead of simply asking if a patient received a specific diagnosis during the interview, a polychoric correlation would consider the underlying frequency and number of symptoms, providing a more nuanced understanding. Some applications to clinical research. The CFA approach allows clinicians and researchers to delve into complex questions like understanding how different symptoms cluster together in mental health disorders. You can tailor treatment plans. By understanding the underlying constructs, we can lead to more personalized treatment plans. It can also aid in early detection and prevention. We can also identify early signs of cognitive decline in aging populations, and insights from CFA can be leveraged to develop community-wide health interventions. Designing a mental health awareness campaign can be targeted to meet specific community needs through these applications. Let's explore a hypothetical study aimed at understanding different facets of anxiety in patients with chronic illness. Anxiety often manifests in various ways, and we'll be looking at 3 facets: physical symptoms, cognitive symptoms, and emotional symptoms. The objective of our study is to develop a valid and reliable 12-item scale to assess these 3 facets of anxiety. We'll be using confirmatory factor analysis to do this. In defining our constructs, we identify 3 specific facets of anxiety that we wish to measure. We have physical symptoms, we'll denote that as PS, cognitive symptoms, CS, and emotional symptoms, ES. Our instrument is a 12-item scale with 4 questions specifically designed to measure each facet. To simplify the model, we group the 12 items into 3 parcels, 1 for each facet, 4 questions for PS, 4 questions for CS, and 4 questions for ES. We hypothetically collect the data from 100 patients with chronic illness, and this sample size gives us the ability to examine our scale's performance. We then clean the data and prepare it for analysis to ensure that all missing values are handled and that the data set is ready for conducting a CFA. We conduct the CFA using statistical software, and this step allows us to test whether the 3 facets correspond to the underlying construct of anxiety. Here's where our findings come alive. The loadings. Most questions are strongly related to their facet. Values close to 1 are ideal, indicating good validity. Cronbach's alpha. The reliability is reasonably high for each facet, suggesting consistent measurement. Correlations. The facets are related but distinct, showing unique contributions to anxiety. Specific values for each aspect provide robust evidence of the validity and reliability of the scale. In conclusion, the hypothetical CFA results suggest that our 12-item scale is a valid and reliable tool for assessing anxiety in patients with chronic illness. By using specific values, we have a clear understanding of how the questions map onto anxiety's facets, and we can confidently use this tool to tailor care to individual patients' needs. This method illustrates how complex psychological constructs can be measured accurately, and it opens the door for future research and clinical practice. In the next video, we're going to look at MTMM as a confirmatory factor analysis using a classical perspective.